Okay, video 3, section 4.2, linear transformations. All right, a linear transformation, recall, is a t from v to w. This is a rule that assigns to each vector in v some other vector t of v and w with two properties. We want, if we apply t to a sum of vectors, it should be the same thing as if we took the applied v individually to each vector and then added it together. This is for all u and v in v. And also the same thing for scalar multiples. It should be the same as if we took the scalar multiple after we applied the transformation t. This is for all u in v and c in the real numbers. Okay. Yeah, so we want sort of corresponding notions to null space and column space, but for linear transformations. Oops, what's happening? Here we go. So definition, the kernel of T is the set of all vectors little v and v with the property that our linear transformation takes them to 0. So this is similar to the null space of a matrix. It's the kernel. And then the range of T is the set of all vectors w, little w, and big W of the form that little w is equal to t of some v for some little v and v. So it's everything that's hit by something from this transformation t. That's our range, and that's related to the column space of a matrix. Both of them are subspaces. The kernel of T is a subspace of V, the domain of T. The range of T is a subspace of W, the codomain of T. So let's do a fun example. And you should always be a little bit dubious if your teacher says you're going to do something fun. Okay, so let's let A and B be real numbers, A less than B. We'll take C1 of AB. This is going to be the set of all functions from the interval AB to R with the property that both f and its first derivative are continuous on this closed interval. Okay, so we've got a collection of functions. And I claim that this collection of functions is itself a vector space because we can add them just by adding pointwise. We can multiply them by real numbers. We have a zero function, a function that's always 0. So that, you can check all the axioms, all the rules that actually C1AB is a vector space. And now we're going to define a linear transformation on this vector space to itself. So we'll define T that'll input a function and output some other function. And wouldn't you know it, we'll define T by taking our old friend, the first derivative. And sure enough, this T is a linear transformation from this vector space to itself. We know this because we know, T is linear transformation. We know that differentiation splits up well over addition. If we take our transformation T and apply it to f plus g, this is totally illegible, so let me tidy it up. F plus g, that's just the derivative of the sum of the functions. We know that the derivative behaves well with respect to addition, and so we can just distribute the derivative. This is the derivative of f plus the derivative of g, but now that's equal to t applied to f plus t applied to g. And so sure enough, our transformation T, defined by taking derivatives, is additive. And similarly, it respects scalar multiplication. T of c times f of x is just the derivative of some constant times f of x, and we know that we can pull constants out. And so this is c times the derivative, and that's just c times t of f of x. Okay, so then we have some huge monstrous vector space. We've got a linear transformation from itself to itself. We can talk about, well, what's the kernel of this transformation? What's the range? Okay, so the kernel of T, this should be the collection of functions f of x in this new vector space, C1AB. And it should be the property that T of f is equal to 0. But we know T of f is just the derivative. Okay, but we know which functions have derivative exactly 0, right? Any constant function has derivative 0. And those are the only functions that have derivative 0. Okay, and we can talk about the range too. Range of t, this should just be, oh yeah, this should be the f of x in C1 of AB, such that f of x is equal to the derivative of some other function, or some g of x in C1 AB. And I'll leave this as a fun exercise. That actually this is equal to all of C1 AB. And you should ask yourself, yeah. Try to justify this for fun. And my hint is try to apply some theorem from Calc 2. We want to say, given some function f here, how do you cook up a function whose derivative is equal to your original function? Okay, and that's all I have to say about linear transformations, column space and null space. I'll see y'all next time with 4.3. Take care, everybody.